Here's the general structure of our generator. The input will be a noise vector Z as before, and the output will be a tanh activated output. This time the output should be of size 32 by 32 by 3, which is the size of our SVHN training images. Because we're using transposed convolutional layers, we'll have no need to reshape a vector output into an image. These layers can output the exact shape that we want. Okay, let's go step by step here. Our generator sees a latent vector Z as input. Then the first layer is going to be a fully connected layer, which is responsible for turning that vector into as many outputs as we want. We'll want enough outputs to reshape the output of this linear layer into a deep and narrow layer, something like 4 by 4 by 128. You can think about this as kind of the reverse process of what we did with our discriminator. After we've shaped the output of our linear layer, next is a series of transposed convolutional layers where you typically halve the depth and double the width and height of the previous layer. And in these cases, we'll apply batch normalization and a normal ReLU activation to all but the last of these hidden layers. At the end of the last layer, we'll apply a tanh activation to get the pixel values that we want. Again, you'll probably want to use at least 3 transposed convolutional layers. Now, most of these transposed convolutional layers will have the same behavior: a transposed convolutional layer followed by a batch norm layer and a ReLU activation function. And so we'll define a helper function to put these layers together. This is just a suggestion, but I would urge you to write a dconv helper function that will create a transposed convolutional layer and append a batch norm layer if the batch norm parameter here is true. This should be really similar to the conv function above. You don't always need to use helper functions like these, but I find that it's a good way to think about the repetition of layers, and in the end, it makes my discriminator and generator class code a little more readable. So I'd suggest that you complete this function, then it will be up to you to use this dconv function and define a complete generator network here. Our generator class takes in a convdim, which should be the depth of one of the last transposed convolutional layers. So back to this diagram, you can imagine this going from a depth of 128 to 64, then 32, and finally a depth of 3 for our output generated image. And you should apply batch norm and ReLU functions to all but the last layer here. Okay, our generator also takes in a Z size, which will define the size of the input latent vector that this generator expects to see. Okay, so try to complete the helper function and this class on your own. And if you'd like to check your work, next I'll go over one solution.